Okay, so if you would just summarize what we had done yesterday. I'm sorry. So we had started looking at the ensembles. What we mean by an ensemble is that we just take many copies, ideally infinite copies of the identical system. Of course, each one of these will be in different microstates. And then we said that, okay, we can represent each one of these as a point in our phase space. So in the phase space, we have what we had called a density. You can say this the mass density or number density, probability density or number density, which is a function of coordinates and position. And then Liouville's theorem stated that in equilibrium, at least, it amounted to saying that rho, whatever its form is, its Poisson bracket with the Hamiltonian of the system, Hamiltonian governing the dynamics of the system, their Poisson bracket should be 0, which basically states that rho is a conserved quantity of the system. Furthermore, we discussed that logarithm of rho, which is also conserved since rho is conserved, should be an additive conserved quantity. Now we said that, okay, so what are the additive conserved quantities we have? One thing is a constant. And if the total volume in phase space was omega, we said that this constant we can define it to be 1 over omega. Omega being the volume in phase space. And another alternative was, this was the microcanonical ensemble. Which is mainly suitable for isolated systems. Here we have an isolated system, meaning that energy is also a constant. And then we said that another alternative might be rho is equal to the exponential of the Hamiltonian, or logarithm of rho could be some constant minus some other constant times the energy. This was the canonical ensemble. And then there's another one that we will see. This logarithm of rho can be constant minus beta E plus beta mu. Mu is some other constant. And this is the grand canonical ensemble. In the canonical ensemble, we allow the energy to change. In the grand canonical ensemble, we allow the energy and the number of particles to change. Now we will study each. Well, we had already studied the microcanonical ensemble, and today we will start studying the canonical ensemble and some of its applications, and later we will be looking at the grand canonical ensemble. Now the question we are asking in the canonical ensemble is, what happens if our system is not isolated, if the energy is not conserved? It can be changing with time. Of course, we will still assume that we will be able to define U. The average energy should be a given value. So instead of a definite value of energy, we will have this restriction that the average should have some value. Now, such a system we can have, for example, if you remember when we were discussing thermodynamics, we were using what we call the heat reservoir. Basically, it's an infinite source of energy. So our system and the heat reservoir can exchange energy. So if we have, let's say, this is our reservoir, this is my system. So this is the kind of system that we would like to study. Now, of course, the system is not isolated, but if we take system plus the reservoir, this whole system is still isolated. If we say the total energy to be E0, this is E plus E prime, where E is the energy of the system and E prime is the energy of the reservoir. So this sum is still conserved. So we can still use the concepts of microcanonical ensemble for this combined system. For my system, I cannot use the microcanonical ensemble because the energy is not conserved. But for the combined system, I can still use the microcanonical ensemble. Now, the first thing I will ask, the question we would like to answer first is, what are the probabilities of a given microstate? Because once we determine those probabilities, we basically calculate everything. So here in this phase space, rho was kind of our probability. Well, before passing, we also had said that omega, at least in the microcanonical ensemble, was omega over omega 0, some unit volume, where we had seen that omega 0 was h to the power 3n. Now, coming back here, so this will be the question. Let's say PR, probability that the system, the small one, is in a state of energy ER. What is this probability? That is what we would like to find. Now, what we can say is, well, the probability is just the number of outcomes that you want divided by the total number of outcomes. So this PR would basically the total number of microstates that the combined system can have. Well, that is, let's say, omega. Let me put C over there for combined system at the energy E0. Well, this, in fact, we can just ignore. This is just a constant, a normalization constant. Multiplied by omega, the number of outcomes that we want would be just the, okay, how many, we are dividing our system into two. So we are looking at the number of ways, number of microstates that the system, the separated systems can be such that my system is in that one particular microstate. Now, this will be just one, that is the outcomes I want for my system, multiplied by the number of microstates that the reservoir has. So the combined system has this many microstates in which my system is in the microstate that I want. So the probability we are looking for will be just 1 times omega for the reservoir of E prime. Well, let me rewrite everything in terms of the energy of my state. Well, this will be equal to 1 times omega of the reservoir of ER, because my system will be in a state which with energy ER. No, sorry, this is E0 minus ER. Divided by omega C E0. Well, omega is a huge number. So usually, rather than expanding, now what we will assume is ER is much smaller than E0, because E0 is the energy of the whole system, which is eventually goes to infinity. ER is negligible, so we can expand this omega R E0 minus ER around E0. But the omega itself is a huge function, so rather than omega, it will be better to expand logarithm of omega R. This will be equal to logarithm of omega r E0 plus the derivative of the logarithm of omega r E with respect to energy evaluated at E is equal to E0 times minus ER. Plus all kinds of other terms. So this will be equal to some constant. You see, omega r E0 is a constant. Its logarithm is a constant. Minus ER. But that derivative is nothing but 1 over kT. Temperature of T being the temperature of the reservoir. Because you see, K times logarithm of omega is what we call the entropy. If you take the derivative of entropy with respect to energy, what you obtain is just 1 over T. So that is how we define the temperature. Plus other terms which go to 0 in the thermodynamic limit. So what we find is omega r E0 minus E of r. This is equal to some constant times e to the power minus ER over KT. Or if we go back to our expression of the probability PR, this is equal to some constant e to the power minus E of r over KT. Well, that constant we can fix by normalization, or we can just calculate it. You see that constant is related to omega c of E0 logarithm of omega r of E0. But that constant, since the probabilities are normalized to 1, has to be e to the power minus E of r over KT divided by sum over all states of my system, small system, e to the power minus E of r over KT. Now that sum is usually what we call the partition function. And, well, what is the average energy? Let's see. The average energy would be just sum over all states, energy of that state, multiplied by the probability of that state, which is sum over all states, ER, e to the power minus beta ER, divided by Z, where I define beta to be 1 over KT, which is 1 over Z times sum over states ER, e to the power minus beta ER. Let me simplify it a bit. If I take the derivative of the exponential with respect to beta, it just brings down ER. So this is equal to 1 over Z minus del over del beta. The remaining sum is nothing but the Z. So what this tells me is the average energy is minus derivative of Z with respect to beta. So once I know Z, for example, I can calculate the average energy. Okay, so this is one way of obtaining these probabilities. Oh, no, sorry, not Z. Logarithm of Z. Now let's try to derive this using ensembles. You see, here we didn't really use the concept of ensembles. Now we have our system in equilibrium. We create our ensemble, which will be basically just many copies of the same system. Now the probability that we were looking at now is just number of copies in the microstate with energy ER divided by n. This is the probability that we are looking for. Of course, in the ideal case, we take infinitely many copies. So we have it, let's just think of it as rolling your dice. If you just roll, you can either roll your dice repeatedly, one after the other, and count how many of the outcomes are the ones that you want, divide by the total outcomes, or just take millions of dices, throw them at the same time, and count how many of them have the outcome that you want. Then by dividing by the total number of dices, you obtain the probability. This is that definition. So I have many microstates. I have the copies of many copies of my state. I look at which ones are in the microstate that I am interested in, divide by the total number of microstates. That gives me the probability that any one of them, any given time, will be in that microstate. Now let me define this as an R over the total number. Now NR of them are NR of them are in the microstate that I'm looking at. Now let us ask the question. How many ensembles, like, let's say this NR, for each state I can assign a number NR. So knowing the numbers NR almost specifies by my ensemble. Almost, not completely. Because I don't really know which one is in which state. I just know that NR of them are in a given state. A different NR prime of them are in a different state with an energy ER prime. That's what I know. Now then we can ask the questions. Given these number NRs, how many different microstates do I have? How many different ensembles can I get? Let me denote that number by omega NR. Just hypothetically assuming, let me just give them some numbers. Shuffling these copies will give me a different microstate, or will give me a different ensemble. Because basically different copies will be in different states now. So it's a different ensemble. How many ways I can shuffle them?
Is it n factorial or nr factorial?
N0 factorial, N1 factorial, and let's say capital M factorial. So I have this many microstates corresponding to a given distribution of microstates. This many ensembles corresponding to a given distribution of microstates. Now the question is, what is the most probable set NR? Let me just call them NR star. But keep in mind, I have several constraints that this NR should satisfy. I will be mainly looking at the maximum of this omega, or logarithm of omega. But when I'm looking at the maximum, I'm not just looking at an arbitrary maximum, I am looking for a maximum that satisfies certain constraints, such as the sum of NR should be capital M. Furthermore, the sum of ER times NR divided by N, which is the average energy. This is fixed. Now keep in mind, the states in my ensemble, they don't need to have the same energy also. They can exchange energy, their energy can change, but the average should be this much. This is a constraint I'm imposing on my system. And then I need to maximize logarithm of omega. I want to maximize omega. So if there are more possible ways that a given NR can be realized, it will be more probable. So omega should be maximized. Again, omega will be a huge number, so it's usually practically better to maximize the logarithm of omega. Well, logarithm of omega will be logarithm of n factorial minus sum of logarithm of nr factorial. Well, you see, n is a huge number. Eventually goes to infinity. In that limit, NR, they also go to infinity. The ratios should be finite, should be fixed. So for both of these terms, I can use the Stirling approximation. N times logarithm of n minus n minus sum over r nr logarithm of nr minus nr. Okay, now this cancels this one. So logarithm of omega is n logarithm of n minus r nr logarithm of nr. I'm looking at the values of nr which maximize this one. Now let me look the variation. So let's assume I just change nr slightly. If it's a maximum, if nr's are such that logarithm of omega is a maximum, a very slight variation of nr shouldn't change its value, the condition of an extremum. Well, the first term is just a constant. This is equal to minus sum over r derivative of nr times logarithm of nr plus nr times the variation of nr over nr. So the variation of the logarithm of omega should be minus logarithm of nr plus 1 times variation of nr. This should be 0. Well, I cannot really set, at this stage, I cannot set the coefficients of delta nr to 0 because they are not all independent. You see, the variations should be such that sum over nr is always n, or sum of the variations should be 0. This is one constraint I have. So that all the variations are not independent. At least this relation relates one of them to the other ones. I have a second constraint. ER times NR should be equal to N times U. This tells me that ER times the variations of NR should also be 0. I have these two constraints. I have these delta NRs that should satisfy these two relations, so at least two of them can be written in terms of the other ones. Now at this point what we do is we just use what's called Lagrange multipliers. So you see, if I just I can just combine all these. And that tells me that sum over R logarithm of NR plus 1 minus alpha minus delta beta ER. No, these are plus. Delta NR, this should be equal to 0. Alpha and beta are just Lagrange multipliers. Now, these are my constraints. I can choose, for example, N0 and N1 and write it in terms of the other ones. Delta N0 and delta N1. And so delta N2, delta N3, and all the other delta N's are independent from each other. Now, if I look at over here, alpha and beta are just arbitrary numbers that I need to choose. Here I just added zeros. But I can choose alpha and beta such that the coefficient of delta N0 and delta N1 is 0. So I have two coefficients that I can just determine randomly, whichever way I like. I just choose them such that the coefficient in the sum of delta N0 and delta N1 is 0. And then the other delta N's, delta NR's, are already independent of each other. I can just change them independently. So if this equality is to be satisfied, their coefficients should also be 0. So at the end of the day, the coefficients of delta NR, all of them should be 0, if this constraint is to be satisfied. So logarithm of NR plus 1 plus alpha plus beta ER should be 0. So I can solve for NR. Now NR star. This is the one that maximizes omega. So NR star should be equal to some constant times e to the power minus beta ER. Well, the probability of the state that has this energy R, the most probable state, let's say, proportional to e to the power minus beta ER again. So again, we obtain the same, basically the same result. Now, there is one thing we will show. Okay, this is the most probable configuration. This is the probability distribution of the most probable distribution. Let's look at what is the average NR. You see, in this averaging, we need to consider all possible cases, all possible configurations of my ensemble. And what I will be aiming at is that this is equal to NR star. So the average of NR will be equal to the most probable NR. And we will also show that the deviation delta NR over let's say NR average is proportional to 1 over square root of n. And keep in mind that this n is the copies in our ensemble, which goes to infinity. So the average NR is equal to the most probable NR. Basically, any other distribution is not really possible, in equilibrium at least. So you see, what we are actually doing over here is we are looking at, we have these multiple copies of the same system. Each copy can have a different energy, can have a different microstate with a different energy. Now what we have shown over here is, for a given, let's say, for a given ensemble, there's a distribution of microstates in my ensemble. So for that ensemble, I can talk about the probability distribution. But then there's another probability distribution. The probability that my ensemble will have that probability distribution. So by maximizing this omega, you see, basically these numbers n r can take any value. They can all be in the ground state, all the copies in my ensemble. All the copies in my ensemble can have an infinitely large energy. Or they can have energy somewhere in between. Half of them can be in the ground state, half of them can have a very huge energy. And what we are saying is they're all equally probable. Each one. Then we are asking the question, what is the probability, these NRs basically tell me the probability distribution through this relation. The probability distribution in one ensemble. That is what NRs are giving me. But of course, there I can construct infinitely many different ensembles. Then the next question is, if I am assuming that each one of these ensembles are equally probable, what is the most probable distribution of these NRs? For a given, this omega is for a given set NR, the number of microstates that have that distribution. That is what I call the omega. Then I looked at the values of NR that maximizes it. So basically I'm looking for the most probable distribution of microstates in my ensemble. And it turned out to be given by this expression over here. This is the most probable probability distribution. Then the next step will be to show these two. That is not just the most probable probability distribution, but it's also the average probability distribution, and the deviation from that average or the most probable goes to 0. So practically there are no ensembles that deviate from that probability distribution. Now let's look at this one. Now this is kind of tedious. I will not do all the steps, but I think it's a nice application of things that you learn in mathematical methods, of course. So what we want to do, this is our NR. This is what we would like to calculate. This is equal to sum over NR omega of that distribution divided by sum over all omega NRs. We are just summing over all possible distributions of my ensembles, which will be equal to Okay, I have nr. Then this distribution I know, n factorial divided by n0 factorial, n1 factorial, etc. And m factorial divided by this sum. Now this is not an easy sum, so let us first do one trick. I will multiply this one by omega 0 to the n0, omega 1 to the n1, omega m. By the way, this m is not finite. In general, because a given system can be in infinitely many microstates. In general, it won't be a finite number. So this 0, 1, 2 is just, it can have infinitely many energies, let's say. N0, N1, N2 is the number of systems in my ensemble which has the energy E0, E1, E2, etc. And of course, in the initial calculation, there is no omega in the result that I'm interested in. So I will just set these omega r's to be 1 after evaluation. Well, the reason why I do that is that, let's say this is nr times, let me just, n factorial, omega 0 to the n0, omega 1 to the n1, divided by n0 factorial, n1 factorial, etc. Well, I need an nr inside the sum. But to get that nr, I can just take that derivative with respect to omega r. That is why I inserted those omegas. So I take the derivative with respect to omega r. That brings me a factor of nr inside the summation. But let me also multiply by omega r, because the exponent will be lowered by 1. So if you look at the original expression, the exponents are n0, n1, etc. If I take the derivative with respect to omega, the exponent will be lowered. So let me just multiply by omega r. It doesn't really make too much difference after we put the omega is equal to 1. And this I need to evaluate at omega is equal to 1. So this will be equal to omega r, del over del omega r. Well, this sum, I'm taking its derivative, dividing by itself, so it will be the derivative of the logarithm. Let me call that gamma. Of course, it depends on the total number of copies I have. It will also depend on the energies I have and also the omegas. So in order to be able to calculate this nr, I just need to calculate that gamma. Well, subject to two constraints. You see these numbers n's. Well, of course, here I'm summing over all possible sets nr. Well, nr's are subject to two constraints. Their sum should be the total number of copies in my ensemble, plus NR times ER should be equal to N times U. I have these two constraints. Now you see, if I didn't have the second constraint, let's call this gamma prime. Well, this is easy to evaluate in the sense that this sum is nothing but omega 0 plus omega 1 plus raised to the power n. Just a multinomial expansion. Of course, assuming that the sum of these nr's is restricted to this capital N. But of course, the problem is now I have the other constraint, that the average energy should be equal to U. Well, the easiest way to get rid of that constraint would be just sum gamma over U. Because if I also sum over all possible values of U, and then sum over all possible sets of NR subject to these two constraints, that will be the same thing as summing over all possible values of NR without that second constraint. Because basically U is also taking any possible value. So I will define, of course, you see, let's see. This is what I want. N factorial. I'm summing over all NR with the constraints that their sum should be fixed, multiplied by ER. The sum should also be fixed. And then I'm also summing over U. Well, eventually I would like to have my sum without the sum over U. So I need to somehow put some means of separating out that term corresponding to a particular value of U. So this is what I will do. I will just multiply this term by Z to the power, let's say, NU. So that for a given value of N, if I just make an expansion of my final sum in powers of Z, if I look at the coefficient of the power Z to the power NU, then I know the sum that I want. Of course, this expression now depends on N and also this number Z. Now that summation is a summation over NR with only the first constraint, not the second one, because I'm also summing over all possible values of U. Now this is Z to the power N0U. Okay. Sum over NR ER. But now without the second constraint, this is nothing but the polynomial expansion of omega 0 Z to the power N0, Z to the power ER, omega 1, Z, no, ER, E1, E0, Z to the power E1, omega 2 z to the power e2, etc. All of this to the power n. And let us just call this f of z. To the power n. This is gamma and z. So I have a closed form expression of this gamma and z. Now what I need to do is I need to obtain the coefficient of z to the power n times u for a given value of u. That will give me the sum that I'm looking for. That will give me this sum over here, gamma. And once I know gamma, I can determine the average value of nr. Okay, there is just one, let's say warning, not warning, but just keep in mind. U, in general, we said that is the average energy. You cannot take the power of something to some power with a unit of energy. So actually, here U is the amount of energy in terms of a pre-chosen unit of energy. So for example, if you have chosen your unit to be electron volts, then U will be 10, for example, for 10 electron volts, or 100 for 100 electron volts. Of course, if you choose a different unit, U will have a different numerical value. Now, why it will be important is, you see, if you look at this sum over here, it's not even a polynomial. You see, in general, n times u need not be an integer. But I can always choose my energy unit small enough such that n times u is always an integer. If n times u is always an integer, this is nothing but a power series expansion. If it is a power series expansion with coefficients, if gamma and z is equal to sum over u, gamma n u, z to the power n times u, gamma n times u will be equal to nz divided by z to the nu plus 1. Well, you see, if I take gamma nz, well, let me put u prime over here. Okay, first of all, I'm assuming that I have chosen a small enough unit of energy such that all the energies relevant in this calculation are integers, integer multiples of that very small energy. And then I'm dividing by, in that case, this is a power series expansion. If I divide by z to the power nu, it's again a power series expansion with positive and negative powers. And gamma nu is nothing but the coefficient of the 1 over z term. But the 1 over z, the coefficient of 1 over z is nothing but the residue of that power expansion. So I can use the complex residue theorem. So this will be equal to, if I take a contour, an integral over a closed contour in the complex z plane and divide by 2 pi I get the coefficient of the 1 over z term, which is the gamma that I'm interested in. So now I have basically converted, you see, initially gamma nu was a complicated sum. Now I converted that into an integral, into a complex integral. So this is equal to 1 over 2 pi I dz of f of z to the power n divided by z to the power nu plus 1. It's a complex integral. The contour it should go around 0. Well, basically, we are looking at the residue at z equal to 0. That's what we are interested in. Its radius should be smaller than the convergence radius of f of z. Well, if it converges, if f of z diverges, the integral is not defined anyway. So it goes around 0. So it's sufficiently small that it avoids the divergence of fz. The only divergence should be at z equal. The only divergence of the integrand should be at z is equal to 0. And hence there won't be any other contribution to that contour integral. Now then the question is, how do you approximate this contour integral? Well, let's look at this function f of z. Oh, let's look at the integrand. So this is the integrand. Let's see what was f of z. Now, I will also make, well, these E0, E1s are the energies of my state. I will choose my ground state energy to be 0, and they're just ordered. I will just assume they are ordered successively. Now, if you look at the function f of z, well, when z is equal to 0, only the E0 term survives. It contributes omega 0. When I set omega to 1, it will be just 1. F of z starts from 1 and it diverges. Let's say omega 0, which eventually will become 1. And as z increases, it should diverge somewhere when you reach the radius of convergence. It can have some complicated behavior, but eventually it will diverge at some point. If you look at 1 over z nu plus 1, this is f of z, let's also put the power n. Now 1 over z to the power nu plus 1 is divergent at z is equal to 1. And it goes to 0. And we have the product of those two functions. Now the product starts from infinity. It starts from infinity. Well, as z goes to infinity, it also goes to infinity. You see, in f of z, you have all powers of z. So the integral is f of z divided by z to the power u. You are dividing by a finite power. But in f of z, you have all the powers. So again, it goes to infinity. But if it starts from infinity and again goes to infinity, it means it basically has a minimum somewhere along the real line. You see, eventually z will be a complex number, but along the real line it should have such a behavior. Let's say it has a minimum somewhere over here. Now, let me just simplify this, not simplify, but rewrite this integral in a slightly different form. That minimum will be important for us. This is equal to 1 over 2 pi I dz e to the power, let's say, minus g of z, where g of z will be equal to minus the logarithm of f of z to the power n divided by z to the power nu plus 1 minus n logarithm of f of z plus nu plus 1 times logarithm of z. You see, the main contribution to this integral will be when, okay, so let's look at g of z. Logarithm of f of z, you see, we said that, okay, g of z. We said that ln of z has a minimum at z is equal to some real number along the real line. It has some minimum. So logarithm of fz also has a minimum at that point. Minus that one has a maximum at that point. Or let me not insert the minus sign over here. This is plus, this is... So ln of fz also has a minimum at that point. Now this is an analytic function as a function of the complex z. It cannot have a local maximum or local minimum. Complex functions cannot have local maxima or local minima. They can at most have saddle points. because they satisfy, analytical functions satisfy Laplace's equation, the real and the imaginary parts. And Laplace's equation cannot have local maxima and local minima. What does that mean? So if you think it as a function of the complex number z, we already seen that it has a minima along the real z. I'm sorry. Along the real z, it has a minima, but that means along the imaginary sets, z, it should have a maximum. So it's a saddle. So we are, you see, we are integrating around such a contour. We said we are integrating around the contour around the z is equal to 0. Well, I can deform that contour such that it goes through x0, and the point x0 is a maximum. So kind of if you imagine what the function looks like along my contour, if this is the x0 point, it looks like something like this. In fact, as n goes to infinity, it will be even more peaked. So this point and this point are the same point. We are basically going around the circle. And we had just seen that since along the real z-axis it has a minimum, along the imaginary z-axis at passing through that minimum, it should be a maximum. This is why we know that there is a maximum over here at x0. But then if it has such a shape, and keep in mind that, as I said, it should be very peaked, well, I can just approximate it by a Gaussian. And that the integral of the Gaussian will be good enough for me, because the Gaussian will take the contributions from that peak, some of the remaining contributions, and that peak dominates the integral. So that will be a good enough approximation. So how do I determine that peak? Well, at that point, this function g prime, g prime, evaluate that x0 should be 0. Well, let's go back. This is our definition of g. So g prime evaluated at x0 will be n times f prime at x0 divided by f evaluated at x0 minus nu plus 1 divided by x0. This should be 0 because it's a maximum. It's an extremum, let's say. And so this tells me that x0, well, also just using that nu is much, much larger than 1. x0 should be equal to, let me rewrite it, since this is much larger than 1. f prime of x0 divided by f of x0 should be equal to u over x0, or x0 should be equal to u f of x over f prime of x0. Okay, this is one relation we know about x0 and the u we have. Okay, then the next thing to be done will be g of z will be g of x0 plus the second derivative of g evaluated at x0 times z minus x0 squared times 1 over 2 factorial plus etc. So now the integral, which is gamma and u, 1 over 2 pi I around my contour of dz e to the power g of x0 plus g double prime of x0 z minus x0 squared times 1 over 2 factorial. I will ignore the other terms. And now, since I'm basically integrating, you see, I'm integrating around a circle. But I said that the most contribution comes from the vicinity of x0. So rather than, okay, it's enough for me to just integrate over that very small segment around x0. That will be more or less equal to my result. Or I can, rather than going around the circle, I can just go from minus infinity to plus infinity, vertical to the real line, as long as I'm passing from x0, because the dominant contribution will be from that point only. And that point I'm keeping fixed. I'm not changing the contribution from that peak. So I can just convert this to 1 over 2 pi I from minus I infinity to I infinity dz e to power g x0 plus g double prime x0 y squared 1 over 2 factorial. Well, this is just a Gaussian integral that you can evaluate. Now, at the end of the day, okay, if you just do these steps, which I will skip, and R turns out to be e to power minus beta ER. Well, in this derivation, you see, up to this point, if you look at this expression, there is nothing called beta. The only thing we have is x0. But what we call x0 is equal to e to power minus beta. This is where the beta enters into this derivation. Yeah, this is just an alternative derivation of basically the same result. In a sense, in these in these last two derivations using the ensembles, we are not using a heat reservoir. But somehow the ensemble itself is the heat reservoir. But still, we basically get the same result. And the final result of all these discussions is that if you have a system that is not isolated, but if it has a temperature T, which, by the way, we just introduce, in all these derivations at least, we introduce to fix the average energy. The temperature U basically fixes the average U. Then the probability of my system to be in a single state R will be equal to, or e to the power minus beta, some parameter, times ER. Energy of that state divided by Z. And how do we determine beta? Well, basically, ER, PR is equal to U determines beta in terms of U. So this is how you determine beta. And it turns out to be 1 over the temperature with a Boltzmann constant. So if we would just sum up, the first method, we just said, okay, we have our system in contact with a heat reservoir. Let's take the combined system, our system plus the heat reservoir, and treat the combined system in microcanonical ensemble that we already know. And then we obtain this probability. In the second approach, what we did was, let's take multiple copies of the same system. This is an ensemble. Energy is not fixed. So practically, there's no constraint on my systems. And so every member of the ensemble can be in one of the infinitely many number of states. It can have zero energy, it can have almost infinite energy, etc. And then we said that, okay, so all the microstates for a given member of the ensemble are possible. So for a given ensemble, there will be a distribution of the microstates. And these numbers give me the number of states in the state specified by R in a given ensemble. And these numbers can take any values. I mean, I have infinitely many such sets. And each such set doesn't uniquely specify an ensemble, because these sets, although they do not really tell me which copy is in which microstate, it just tells me the number of copies in a given microstate. But doesn't tell me which one is which. So to each such set, this much ensemble, there are these many ensembles corresponding to each given set NR. And just using this a priori equal probabilities, we are saying that every ensemble is equally probable. There's no restriction. And saying that every ensemble is equally probable just tells me that the probability distribution of these numbers NR correspond to the number of ensembles which have those numbers NR. And then we ask the question, what is the most probable value of these set NR star? And NR star turned out to be proportional to e to power minus beta ER. This is our NR star. This is the most probable distribution. And then we said in the third approach, well, it's not really a third approach, but the continuation of the second derivation. We looked for, okay, so I have infinitely many possibilities for my ensemble. What is the average NR? Not the most probable, but the average. And it turned out to be equal to the most probable one. Okay, in your book there is the derivations, all the detailed derivation, but I think it kind of gets boring after some time. So this is what we obtain. Furthermore, the deviation turns out to go to 0 as you take the ideal limit of your ensemble with infinitely many copies. And this result will be what we will be using next when we are studying systems in using canonical ensemble. Of course, the first thing is, okay, so you see, we have these probability distributions, but what about the entropy, or I don't know, the pressure of the system? How will we get those? That is what we will look next week. Questions? So see you next week.